Metamorphism. Introduction. Metamorphism mineralogical and structural adjustment of solid rocks to physical and chemical conditions differing from those under which the rocks originally formed. Changes produced by surface conditions such as compaction are usually excluded. The most important agents of metamorphism include temperature, pressure, and fluids. Equally as significant are changes in chemical environment that result into metamorphic processes. First, mechanical dislocation, where a rock is deformed, especially because of differential stress. Second, chemical recrystallization, where a mineral assemblage becomes out of equilibrium due to temperature and pressure changes and a new mineral assemblage form. The word metamorphism comes from the Greek meta means after, morph means form, so metamorphism means the after form. Three types of metamorphism may occur depending on the relative effect of mechanical and chemical changes. Dynamic metamorphism result mainly from mechanical deformation with little long-term temperature change. Textures produced by such adjustment range from breccias composed of angular shattered rocks fragments to very fine grain, granulated or powder rocks with obvious foliation and lineation. Large pre-existing mineral grains may be deformed because of stress. Contact metamorphism occurs primarily because of increases in temperature where differential stress is minor. A common phenomenon is the effect produced adjacent to igneous intrusion, where several metamorphic zones represented by changing mineral assemblages reflect the temperature gradient from the high temperature intrusion to the low temperature host rocks. Those zones are concentric to the intrusion. Because the volume affected is small, the pressures are near constant. Resulting rocks have equidimensional grains because of a lack of stress and are usually fine grained due to the short duration of metamorphism. Regional metamorphism results from the general increase, usually correlated, of temperature and pressure over a large area. Grades or intensities of metamorphism are represented by different mineral assemblages that either give relative values of temperature or absolute values when calibrated against laboratory experiments. Regional metamorphism can be subdivided into different pressure temperature conditions based on observed sequence of mineral assemblages. It may include an extreme condition where partial melting occurs called anactesis. Other types of metamorphism can occur. They are retrograde metamorphism, the response of mineral assemblages to decreasing temperature and pressure. Metasomatism, the metamorphism that includes the additional or subtraction of components from the original assemblage. Polymetamorphism, the effect of more than one metamorphic event. And hydrothermal metamorphism, the changes that occur in the presence of water at high temperature and pressure which affect the resulting mineralogy and rate of reaction. Body. The process of metamorphism does not melt the rock, but instead transform them into denser, more compact rocks. New minerals are created either by rearrangement of mineral components or by reactions with fluid that enter the rocks. Boreal metamorphism. a type of very low-graded metamorphism, which result from partial to complete recrystallization of deeply buried sedimentary and volcanic rocks at depth and temperature more than 10 km and 200 to 300 degrees Celsius respectively, and along low to medium PT ratios. At deeper levels of boreal metamorphism, there is circulation of hot hydrous fluids at an elevated geothermal gradient. The metamorphism overlaps with hydrothermal metamorphism. Boreal metamorphism under extensional tectonic setting, such those in the Welsh Basin, Southwest England Basin, and English Lake District with characteristic anticlockwise PT paths, was given the term diathermal metamorphism. Contact metamorphism. At shallow depths within the crust, usually less than 6 km, the heat sources responsible for contact metamorphism are bodies of hot magma which raise the temperature of the surrounding rocks. These thermal effects are usually restricted to the contact zone of the intrusion, hence the term contact metamorphism. However, sometimes hot fluids are released from the intrusions and penetrate the enclosing rocks along fractures and produce contact metamorphic zone. Basic magmas are much hotter than acid magmas and hence will have greater thermal effect. Also, a large intrusion contains much more heat than a small day-like body, and its effects on the surrounding country rocks will be much greater and more widespread. Rock adjacent to thin dikes and sill are simply baked and hardened and do not experience any great mineralogical. Larger plutons gives rise to contact zone within which the country rocks are thermally metamorphosed. As large plutons take millions of years to cool down, the surrounding country rocks are also stay hot for tens of thousands of years, allowing chemical reaction to continue to completion. Dynamic metamorphism. Dynamic metamorphic rocks are restricted to narrow zone adjacent to faults or troughs. The high shear stress associated with faults and troughs crash to adjacent rocks. The rise in temperature is produced by frictional heat generated within the fault line zone. The high shear stress may be short-lived or long-lived depending on the activity of the fault or truss. Dynamic metamorphism involves high shear stress, high pressure, high strain, high fluid partial pressure, and variable temperature. In many instances, water plays a fundamental role.
Regional metamorphism. Most metamorphic rocks occurs in fold mountain belts or cratonic areas. Such rocks cover large areas of Earth's crust and are therefore termed regional metamorphic rocks. They arise by the combined action of heat, boreal pressure, differential stress, strain, and fluids on pre-existing rocks. The resulting rocks are always deformed because of the differential stress and commonly exhibit faults, fractures, and cleavage. Large amounts of granitic intrusion are also associated with regional metamorphic rocks. The most common regional metamorphic rocks are slates, schists, and gneisses. Regional metamorphism covers a wide range of temperature and pressure conditions from 200 degrees Celsius to 750 degrees Celsius and 2 bar to 10 bar or 5 km to 35 km depth. There are three metamorphic phases within regional metamorphosed rocks, which from lowest to highest grade are green cysts, can be further divided into chlorite and biotite zones. The term green schist gets its name from the rocks themselves, as many rocks of these phases are gray-green in color and have schistose. Amphibolite can be further divided into carnate and staurolite zone. The term amphibolite gets its name from most common constituent minerals of these phases, minerals of amphibole group. Granulite can be further divided into kyanite and sillimanite zone. The term granulite reflects the most common texture of these rocks, granular.
Hydrothermal metamorphism. Rocks that are altered at high temperatures and moderate pressures by hydrothermal fluids are hydrothermally metamorphosed. This is common in basaltic rocks that generally lack hydrous minerals. The hydrothermal metamorphism result in alteration to such MgFe rich hydrous minerals as talc, chlorite, serpentine, actinolite, tremolite, zeolites, and clay minerals. Rich ore deposits are often formed because of hydrothermal metamorphism. Shock metamorphism. When an extraterrestrial body, such as meteorite or comet, impacts with the Earth, or if there is a very large volcanic explosion, ultra-high pressure can be generated in the impact rock. This ultra-high pressure can produce minerals that are only stable at very high pressure, such as the SiO2 polymorphs, chaosite, stiovite. In addition, they can produce textures known as shock lamellae in mineral grains and such texture as shatter cones in the impact rock. High pressure metamorphism. In some parts of the world, geological young fold mountain belts contain sequence of metamorphosed fine-grained sedimentary rocks and basic volcanic rocks that contain unusual blue amphiboles. Cataclysmic metamorphism. Cataclysmic metamorphism occurs as a result of mechanical deformation, like when two bodies of rock slide past one another along a fault zone. Heat is generated by the friction of sliding along such a shear zone, and the rocks tend to be mechanically deformed, being crushed and pulverized due to the shearing. Cataclysmic metamorphism is not very common and is restricted to a narrow zone along which the shearing occurs. Conclusion. Metamorphisms involve the solid-state processes by which rocks adjust chemically and texturally to conditions that differ from those under which they initially formed. The principal agents of metamorphism are temperature, pressure, infiltrating fluids, and deformation. It is generally accepted that some metamorphic rocks can be created by simple burial to sufficient depth. Rocks now exposed at the surface were affected by some additional process such as mountain building, alteration by an adjacent igneous intense deformation. A series of metamorphic rocks may thus be revealed that were exposed to differing grades of metamorphism. One might then walk across rocks ranging from unmetamorphosed into progressive higher metamorphic grades. The pre-metamorphic parent rock is called the protolith. The protolith temperature and pressure of metamorphic equilibration and effects of deformation are the principal controls governing the result rock and its name. Understanding the relation between the metamorphic rocks and the protoliths of each further allows a researcher to infer such things sedimentary environments that exist prior to a metamorphism. When combined with age-dating the structural analysis, the geologic story, history of various areas can be interpreted.